In Module 1.5, we will go over programming languages for scientific computing. Now, you might be wondering, do I need to be a programming expert to succeed in this course? The answer is absolutely not. However, learning the basics of the programming will definitely help in this course. Some of the topics that we are going to cover in this course are introduction to programming languages, what is a programming language, different types of programming languages, data structures, data handling such as importing, exporting data, how to handle data, and very importantly, how to visualize the data. Object-oriented programming, parallel and high-performance computing, which are necessary for real-life application of simulation methods, numerical algorithms to solve ODEs and PDEs that we covered in the previous module, what is software repositories, notebooks, and GitHub. So what is programming? Programming is a process of designing and building an executable program to accomplish a specific computing result or perform a particular task, such as adding two numbers, multiplying two numbers, solving equations, and so on. A programming language is a formal language comprising a set of instructions that produce various kinds of output. So you might write a program to add two numbers. Now it will produce outputs which are the sum of a couple of numbers or many numbers, for example. Some of the key concepts in programming languages are syntax and semantics. So just like natural languages, programming languages also have a set of rules, and they are characterized by syntax. For example, Python versus C versus MATLAB. These are the examples of different types of programming languages, and how we define if statement, for statement, and so on will differ based on what kind of programming language that you're going to use. High versus low level languages. So high level languages such as Python, MATLAB, Java are more abstract and provide syntax that is closer to human language, and that's why they are very easy to get started with. However, low level languages such as C are close to machine code, and that's why they are sometimes difficult to get started. Static versus dynamic typing. So languages also differ in how they handle data types. So for example, in C, the type of variable is known at the compile time. In dynamical type languages as Python, they are determined at the runtime. Same compile versus interpreted. Some of the languages are compiled, such as C, while others are interpreted, such as Python. Some of the key data structures. So these are very important as we move forward in the course. For example, variables. So this is variables which are used to store individual data. In a mechanical context, they could be represent various physical parameters such as engine temperature, shift speed, and you can see that we are defining variable, and we can also print it, such as the engine temperature is this Celsius. Arrays and lists. Sometimes we don't have only single value data, such as 150, we will have multiple such data. That's why we store them in a arrays and list. So an array is a collection of elements useful for storing data types of the same type. So same type here means like all of them are numbers. A list could have, on the other hand, a collection of numbers, characters, and so on. So that's the difference in a way. Sets. Set are used for storing unique items such as A1, A2, B1, A1. Here, A1 is duplicated. So if you just ask for the set of this, it will give you A1, A2, and B1. Dictionaries are very important for programming languages, and these are collections of key value pairs. So suppose you are trying to define a material properties. So you can have steel's material properties with your density and Young's modulus. Similarly, for aluminum, you have density and Young's modulus, and you can see this steel versus aluminum. You can compare them based on this dictionary data, and you can easily print it, you can easily access it, and so on. Now, some of the important concepts for programming is using your own data or using a custom data for the programming language. For that, we need to input our data from files. And for that, we need to learn how to import data in Python. So for example, here we are reading a CSV file or Excel file or comma separated file where the columns are timestamp, sensor 1, sensor 2, and sensor 3 readings. So they are separated by comma here. You can see that's why it's comma separated files. And you can read them using pandas. You can calculate the mean or average of these numbers for this column and so on. So these are very useful. Other than reading them, you can also plot them. So in the first part here, you see that we are trying to read the data, and the second part on the right-hand side, we see that we are trying to plot the timestamp versus sensor 1 data, sensor 2 data, and sensor 3 data. And we're also trying to provide the X and Y labels. Now, let's move on to object-oriented programming. So object-oriented programming is used for storing objects. So it centers around three main concepts: classes, objects, and inheritance. So a class is kind of blueprint of creating objects. A class defines a type in terms of its data and its behavior, such as attributes and methods. Objects, an instance of a class. When a class is defined, no memory is allocated until an object is created. That's very powerful because it helps you kind of use as a container of the entire module that you are working with. Each object can hold different data, but they shared structure and behavior defined by their class. So for example, here is we are trying to have a class for machine components. So initialize this class init with the self.material. So it has a material kind of as the particular attribute. And it can also have methods such as this def, display materials. So here we are trying to display the component material is self.material. Or you can have another example such as bearing, which can be a inheritance of the machine components. So this also have init or initialization with the bearing type. And when you display, it also inherits this display materials kind of because it was inherited from the machine component. As we go through this hands-on session, we'll try to learn more about this programming caveats and techniques. Now you can run this course on a single computer, but for modern materials modeling or multi-skill modeling, you need high performance computing. And that's why it's important to learn about parallel computing. Parallel computing involves dividing the large problems into smaller ones, which are then solved across multiple processing units. These units could be CPUs or GPUs. So we'll talk about that. So it can have data parallels or it can be task parallel. So you want to distribute the amount of data you have across multiple cores, or you can, instead of doing data, you can also do it in terms of tasks. So depending on the problem that you're trying to solve, one versus other could be chosen. Some of the key concepts of HPC are, HPC is a way to harness the power of parallel processing to run advanced applications for efficiency and reliability. And this often involves using supercomputers or computer clusters. So supercomputers are extremely fast computers, and these are usually a facility from a national lab, from a company, from a university, and so on. And clusters are also a very similar way, but they're maintained by a smaller group of individuals and so on. So parallel algorithms, so algorithms specially designed to exploit parallel architectures, message passing interface, MPI, a standardized way to message pass across parallel computers. OpenMP is an API that supports or application programming interface that supports multi-platform shared memory across C, C++, Fortran. For GPUs, especially CUDA, Compute Unified Device Architecture, is a parallel computing platform and API module created by NVIDIA company. So it allows software developers to use CUDA, which is that we just defined, to enable graphics processing unit. And it's very popular nowadays. Now you might want to kind of schedule your jobs, and for scheduling your jobs or high performance computing, you might use schedulers such as Slurm or PBS. So here's an example for calculating factorial using single versus parallel computation. So on your left-hand side, we import Python libraries, math, and the time, and def is basically a method or a function. So here we try to compute factorial for a given number. So math already has a function like that. We can calculate that using serial factorial. So where we have numbers, and for each of these numbers, we try to append or extend the list. So the result is a list here. So here is the example. Suppose 5, 7, and so on are the list of numbers, and we want to calculate the factorial of these. So we can just pass it to the serial factorial methods, and we can calculate from the time how much time did it take to perform this task. Now this was single processor. You can also accomplish this task using parallel computers. So here we are using 2 cores, for example, and we are using the multiprocessing from Python tool. So this pool will now kind of have 2 workers to process this task. And then we can similar way like we did for the serial programming. So we can have parallel factorials, and we can also compare the task of CPU versus GPUs. So we talked about serial versus CPUs, but we also want to learn about the GPU programming. So in GPU programming, you might have libraries such as PyCUDA. And for that, suppose you want to compute squares of numbers, you can simply compute it on CPUs using **2, which is square. If you want to do **3, that's cube, and so on. And if you want to do this on GPUs, you might have to define the variables, such as the what is destination variable, what is an input variable, and so on, and how does the message propagates so over GPUs. So this can be cumbersome, and that is why simple CPU-based programming languages are more popular, but for high-performance computing, GPU kind of programming are more important. You can also compare the CPU versus GPU performance, so you can generate several millions of the random numbers and calculate the square of the numbers, and you can compare their timings. Now, these were the simple exercises. Now we'll move on to solving ordinary differential equation, especially a damped harmonic oscillator given by this equation. We had seen this equation in the previous module. So where m is a mass, d2x dt square, also represented by x double dot, is the acceleration, gamma is a damping factor, dx dt is the velocity, and omega is the frequency, and so on, and equal to 0. So in order to solve this equation, we will use the ODE int from SciPy library in Python, and we'll plot it using matplotlib library, and NumPy is a library to manipulate different arrays in Python. So very simple. We'll start with the damped harmonic oscillator, which has the variable state, time, the gamma, and the omega that we saw in the equation, and we'll define x, v as a state, dx dt is kind of the first order derivative, and dv dt is kind of the second order derivative. And given the state, t, gamma, omega, we can now return this dx dt, which is the velocity, and the dv dt, which is the acceleration. Now we have to define some damping coefficients and other coefficients for solving the equations. Now, depending on the system that you are working with, these variables might change. So we can start with x0, v0 as 1 and 0. This is my initial conditions, initial displacement, initial velocity. And now we want to define over what range of time we want to solve this. And then we give it to the ODE int library, which will solve this. And now we can plot how does x and v look like. And here you see a nice plot of x, which is the position, and v, which is the velocity. Now, similarly, we can use this for solving a one-dimensional heat equation. So we will use the ODE int. We'll define some parameters such as the length of the rod, how many points along the rods, the diffusivity of the rod, and etc. And this can be material dependent. And we also important to learn about the boundary conditions. So if you want to solve this equation of one-dimensional heat equation, we also might impose certain fixed temperature on both of the ends of the rod. And then we can define the time. And then over the ODE int, we can try to solve the this particular equation. And the solution will look something like this on your right. While the solution was on one dimension, we might want to extend it to 2 and 3 dimensions. So here is an example for 2-dimensional case. Here, in addition to have Lx, we have Lx and Ly, so it's a plane. And similarly, we have to define the number of spatial points. So these spatial points are important to kind of discretize the sample space or the space of the plane, and some other material parameters, the discretizations, the length, and in x and y, what kind of boundary conditions in x and y you want to have, heat equation, which is coded in this kind of way. You can see this is the finite difference kind of solution that we learned in the previous module, where we are trying to solve the du dt alpha del 2 del x square and del 2u del y square. And similarly, we solve this, and now we can visualize this also in using matplotlib in Python. So here we are using Python mainly throughout the course, but it can be easily converted if needed in MATLAB or in C++ or any other languages. Now we'll solve a 2D Laplace equation for steady state heat distribution in a rectangular plate with specified boundary conditions. So very similar to the previous case, we have specified the number of grid points, specified the boundary conditions, and we try to solve this equation, and you can visualize this in Matplotlib. Now moving on to another problem where involves matrix. So you'll use the matrix library called NumPy, linalg or linear algebra library. So suppose we have a symmetric matrix for a stiffness matrix of a 3-mass system. This is the 3-mass system you can see on your right, which are connected by a spring, and the spring has a spring constant, where each mass is connected to its neighbor by a spring, and the boundary mass are connected to a fixed wall. So there you can see if we define an arbitrary example stiffness matrix like this 3x3 matrix, then we can solve the matrix and get the eigenvalues and eigenvectors that we learned in the previous module using NP-linalg EIGA, and that will give you the eigenvalues and the eigenvectors. And we can also plot them as on your right-hand side, the eigenvalues of mode 1, mode 2, mode 3. And these are especially useful for dynamical analysis and vibrational analysis of a mechanical system. Now, we move on to the software repositories, GitHub and Jupyter Notebooks. The software repository, mainly represented by a repo for short, is a storage of location for software packages. So for example, I can create several Jupyter Notebooks or Python program and just store in my personal laptop, or I can upload in a GitHub, which is a kind of the repository platform, a cloud-based hosting platform. So here I have, for example, created a MMSM, multi-scale modeling and simulation from mechanical system kind of repository. And I have uploaded several notebooks there. So what is a notebook? So you can do programming using a typical editor, but sometimes it's useful to use web application and you can interact with it. So that's why Jupyter notebooks are useful. Now, sometimes installing some of the softwares on local computers can be quite tedious. So that's why there are cloud-based Jupyter notebooks such as Google Colab. So I'll upload this example, and then you can click on the open in Colab and it'll open this notebook, and you might have to log in with your Gmail, and then you can execute each block. So basically shift enter or just press the play button on the left-hand side of each block and it will execute the instructions. So this is it for this module.